Welcome to Quantum Computing Essentials Part 1, Lecture 6. So, in this particular lecture, today we'll be discussing about the topic we can name as a spatial matrices. Okay? Spatial matrices. Because these matrices have some properties which are very important for us. So, for this class of spatial matrices, we'll be discussing about the unitary matrix and the orthogonal matrices. Orthogonal matrices. Will define a particular category of matrix known as the normal matrix. Normal matrix. Then we will discuss about some other matrices like the symmetric and Hermitian matrices. Okay, symmetric and Hermitian matrices. And Hermitian matrices. Hermitian matrices. We'll discuss about the positive semi-definite matrix or the PSD matrix. So these are very some of the very special matrices with properties are very important and we'll be using frequently in the quantum literature. So first, let us first discuss about the unitary and orthogonal matrices. Okay. So the first part is the unitary and orthogonal matrices. Orthogonal matrices. So these matrices have certain properties. Okay. So unitary matrix is basically a complex matrix. Okay. So unitary matrix is basically a complex matrix UN cross N of some dimension N cross N. So basically they are complex matrices, means they belongs to Cn cross N. I took square version. You can also take the M cross N as well, no issue. So where the columns or the rows, they constitute orthonormal basis. So where the basically every the column, say you can write it as this. Suppose this you can write it as U equals to U1 to up to UN number of vectors. So these are the column vectors, for example, U1, U2 to UN. Okay. So all those column vectors, they basically constitute. So all UIs constitutes constitutes an orthonormal basis. Orthonormal basis. Orthonormal basis for Cn. So we defined orthonormal sets, right? So orthogonal matrix. So an orthogonal matrix So sometimes represented by capital O notation. Okay. So we take, say, for simplicity, a P notation. Okay. So is some matrix P n cross n, P n cross n. So which columns constitute orthonormal basis? So this P cross n, basically they are the real matrices. Okay. So they should belongs to R some n cross n. Here I have taken the square matrix cases. So you can as take uh, the rectangular matrix as well. So here, if you can represent your capital P matrix n cross n by the columns as, say, P1, P2 to up to Pn, they are the columns. Okay. So then basically what you have is, so every Pi, these vectors, they constitutes some orthonormal basis, constitutes an orthonormal basis for Rn. Okay. So real vector space and this complex vector space of dimension so and so. So we have some notes. So first of all, the orthogonal matrices and unitary matrices have some nice properties. So if you have some vector ui, okay, so I can take it as this get notation. So ui inner product with uj, if you do, okay, this thing you can do this side also like this. So if you do the inner product of this two, so you will get the delta ij function. So that means they will be equals to 1 if I equals to j, and equals to 0 if I not equals to 0. So this is the first means they are the orthonormal basis vectors. Okay. So it implies that if you have the matrix U, which takes all these UIs or UJs as the columns, then if you do the conjugation and multiply it with another matrix Q, so what effectively will get, the similar element will be giving you 1, the result 1, and the dissimilar these vectors will give you 0 element. So ultimately you will get an identity matrix. Okay. So, and again, if you do the multiplication like this, so you use this. So you get the same result, the identity matrix, because of this property. Okay. The second property is so here the conclusion is the columns of U are orthonormal, uh, and which implies that rows of U are also orthonormal to satisfy this particular property. This is the property. It's a very important property. So as you will see that if we have quantum state chi1, okay, and we try to evolve another quantum state chi2, okay. So if there is an evolution, and if it is defined by some operator, say for example it's an operator v, and there is a reverse path, say for example if you want to come back to this chi2 to chi1, and there is another path, say v prime, then this v should be an unitary operator. That means it should satisfy this identity. So we'll again define another term called isometry, which is a general class for this. So this is a very important formula. So formula means a property for this unitary matrices. Secondly, the another property is that if you multiply this unitary matrix with any vectors, not necessarily a unit vector, any vector kx, x vector, not just kx. So if you take the square, okay, so you will, what effectively will be getting is that so it is basically the conjugation of x into u, conjugation into u into x. So this is the vector, this is the vector, and the overall to norm. So this is the thing that for which the result is identity, and if you multiply an identity with the vector x, it will give you the result x. So effectively you will be getting this norm of x square. Okay. So for any vector compatible with the multiplications with you, so for any vector belongs to Cn, this should be satisfied. Okay. So this is called the norm preserve property of the unitary operator. So norm preserve property, okay, or trace preserve property of the norm preserve property of this unitary operator. So the conclusion is multiplying uh, multiplying an unitary operator u, okay, to a vector does not change the length of the vector x. Okay, so multiplying a vector u to a vector say x does not change the length of x. So this is the conclusions. However, so as this matrix is a complex matrix, there is phase information. However, it can change the direction. This is very important. So if you multiply u to a vector, however, it can change the direction. It can change the direction, means phase of this vector. So when we'll be diagonalize a matrix, say for example through eigenvalue decomposition or singular value decomposition, this kind of multiplication we'll see. Means if you have a vector like this, get say example, it's a vector x in some arbitrary system. So if you multiply this particular vector or a quantum state with a unitary matrix or evolution U. So effectively, you may come across to this typical vector. Say, for example, this vector, it will be some vector x prime, but the the length of x prime and the length of x should be same. Only this angle may be different. So if it is some theta 1, it can be some theta 2, and just this is a product of some unitary matrix U. Okay, so you have done this particular evolution, or the product of the product of a unitary matrix with the state x to get the another state x prime. Okay, uh, but in case of eigenvalue decomposition, the direction is unchanged. Okay, amplitude of x is changed. That is very important. Okay. So in case of eigenvalue decomposition, we'll see that if you have a matrix X, there is some eigenvector X for which you get some scalar with this particular vector X. So this is the eigenvalue lambda. So any particular lambda it can be, provided X is not equals to 0. If it satisfies, then it's an eigenvalue. And you will see that basically multiplying this any matrix with X, if you get the result lambda X here, basically you this particular X is multiplied with a scalar factor lambda. Okay, but here direction is same. Suppose X is like this. Okay. And if you multiply with the matrix in the eigenvalue decomposition problem, it will stretch the vector and it will keep this theta constant. Okay, but here the theta is changed, but length is constant. Okay, this is the key difference in multiplications with a unitary matrix and the eigenvalue problem. Okay. So some more characterizations we'll see for the unitary matrices. So because unitary matrices are in the left and right side everywhere in the quantum literature. So some characteristics. So we have properties like here, the number is 2, right? So we have 3. So note that U inverse, if you have some unitary matrix, its inverse will be actually only the conjugation, complex conjugation, nothing else. Because we know U star U is the identity, which is also equals to U star, U star, right? So in this case, so U star is basically what you. So if you pre-multiply, post-multiply like this, so U star U into U inverse will be identity into U inverse, right? So this is what, this is identity again, and this will be U inverse. So it implies U stars equals to U inverse. Okay. So this is a very important property. So if you have some kind of inversion problem, so if it is an unitary matrix, you just need to do the complex conjugation and nothing else. Okay. And for a orthogonal matrix, the same property what P inverse equals to P transpose. Okay. Here you do the transposition operation. Here complex transposition, conjugate transposition. Okay. So this is another important property. So another note is that the identity matrix and and then the permutation matrix. The permutation of the rows of I will give you the permutation matrix, rows and columns. The identity matrix and permutation matrices are actually orthogonal matrices. Are orthogonal matrices. Okay. Uh, One another definition, just we can have a discussion more on this particular thing. Just for the definition, I'm defining a particular term known as isometry. Isometry. What is an isometry? As a linear, if a linear operator, linear operator T on a vector space, V, if it satisfies the property that norm of T into some x vector equals to the vector x for all such vectors belongs to the vector space V, then we call that it's an isometry. It's an this linear operator. It's an isometry. Is an isometry on V, and uh, the isometries on Rn, the isometries on Rn and Cn are precisely known as the orthogonal and unitary matrices. Respectively. Okay, so we'll define certain things regarding some other matrices as well. So the first thing we'll be discussing about the normal matrices. The normal matrices. So if a matrix A, it's some matrix, say it's some complex matrix, for example, if A belongs to Cn cross N, is unitary diagonalizable. How to diagonalize a matrix we'll discuss on some future lectures. So for the time being, consider that this matrix is unitary diagonalizable. Diagonalizable to the diagonal matrix D. Okay. So that means A will have that is the A matrix will have a complete orthonormal set of eigenvectors. So if and only if A star A equals to A star. If for certain matrices this property hold, so that product of the conjugation with the matrix or equals to the product of the matrix with its conjugation, if they are the same result, then A matrix is called a normal matrix. Then A is called a normal matrix. normal matrix. For this kind of matrix, EVD always exists. Okay. Eigenvalue decomposition will read at some point of time what is eigenvalue decomposition. This particular decomposition always exists for the normal matrix. Okay, always exists. So uh, let us define some more matrices. The symmetric, so some properties we can discuss, right, for simplicity, for the symmetric and the and these the Hermitian matrices. Okay. Hermitian matrices. So of course, if any matrix A is transpose of A, then we say it's a symmetric matrix. Similarly, for the A Hermitian matrix, if A is its complex conjugate, so we have a definition for this as the Hermitian matrix. These two together can be written as A equals to A dagger. Okay. So these dagger notation sometimes we will come across in certain scientific paper, dagger notation. So it implies both the symmetric and the Hermitian property together. Okay. So in addition to all properties of the normal matrices that we discussed, so real symmetric and complex Hermitian matrices have they have a very good important property is that, so for this kind of matrices, all the eigenvalues are real. So it's a homework for you all to prove that the eigenvalue for a symmetric or Hermitian matrix is a real quantity. Okay. So it's a problem for all of you. It's a very simple proof, but you should try this. Then if A is a real symmetric, so to note here, if A is a real symmetry, if A is real symmetric, um, a matrix A is real symmetric if and only if A is orthogonal. A is orthogonal similar to a real diagonal matrix. A real diagonal matrix D such that the P transpose A into P equals to D. This is a very important property. This is a very important property for some orthogonal matrix P. For some orthogonal P. Orthogonal matrix P. Then we have another property. Um, So if we have the skew symmetric matrix, maybe real or complex, real skew symmetric or skew Hermitian, skew symmetric matrix, skew symmetric or skew Hermitian or skew Hermitian matrices. So what is a skew symmetric matrix? So basically, if you have a matrix A, okay, if it is equals to the minus of A transpose, so it is, we call it as a skew symmetry. If A equals to your minus of A star, then this kind of matrices we call the skew Hermitian matrix. Then basically, all the eigenvalues of this kind of matrices are eigenvalues are eigenvalues are pure imaginary. Okay. Here we had real, here we have pure imaginary. Okay. So some complex number with pure imaginary part will be there and no real part. So the last part here, last but not the least, one is the positive semi-definite or the PSD matrix. So this is one of the most important matrices, which is known as the positive semi-definite. Sometimes we'll come across definite. So here it is positive semi-definite. Positive semi-definite PS and T PSD matrix. PSD matrices. And the positive definite are called PD matrices, positive definite. So, so for some real symmetric or the Hermitian matrices A, for some A, okay, that may belong to some R, say for simplicity we take n cross n, or it may be some complex as well, n cross n, and they should be real symmetric matrices or the Hermitian matrices. Okay, so they should be real symmetric that means A equals to A star or A transpose symmetric or Hermitian. Hermitian matrices. Then uh, there are certain properties for positive definiteness. Okay, so what are the properties? The first one is if for some vector uh, x, the x transpose ax, okay, if it is greater than 0, okay, so for this kind of vectors can be real or complex, okay, there may be some field defined of dimension n, okay. So then basically this A matrix is called the definite, positive definite matrix, okay. Or if there is this greater equals to, then we'll call it as a PSD matrix. So in quantum, we can write it as, so A is this, then you have this kx and this side as x. If this particular quantity is greater equals to 0 with Dirac notation, then we called this particular operator. A is an operator here. A is a PSD operator, positive semi-definite operator. Operator. Okay. So secondly, for all such PSD matrices, okay, all the lambda I, they are the eigenvalue. That means they belongs to some, they belongs to the spectrum of A. If they are greater equals to 0, then basically this A matrix is called the PSD matrix. So for a PSD matrix, the eigenvalue should be either 0 or more than 0. If it is a PD matrix, then it should be sharply greater than 0. So then third property is a very important property, is that if A, the matrix, you can write it as product of B transpose B, two matrices, B and B, for some non-singular, for uh, some non-singular, for some non-singular matrix B, ordinary matrix. So you can represent like that for a PSD matrix. And if this B matrix, if this B is actually R, where R is some upper triangular matrix, there B is some ordinary matrix. If it is R, some upper triangular matrix, that means the matrix will look like this. So the elements will be like this, and all rest will be 0. So this kind of structure. Then A you can write as R transpose R. Okay. This particular decomposition or the breakup of the matrix is known as Cholesky decomposition. Cholesky decomposition. So for any PSD matrix, Cholesky decomposition must exist. So Cholesky decomposition should exist for any PSD matrix. Okay, and eigenvalue decomposition should exist for any real normal matrix. This is a very important fact. Then so there are some minor properties like leading principal minors of A should be positive, all the principal minors of A should be positive, and this some other properties are there, so which we can see at some other point of time. So this is for now as a case of special matrices. So so in summary, here what we have learned about the unitary matrices. Then we have learned the orthogonal matrices. So we learned about the normal matrices, the normal matrices, and the symmetric and Hermitian matrices, and some properties of the of such matrices, symmetric and Hermitian matrices. And also we come across the PD and PSD matrices. PD and PSD matrices, positive semi-definite and positive definite and positive semi-definite matrices, and some of its properties, its eigenvalues and all. Okay, so in the next lecture, we will come across some other special matrices which can act as an important operator, such as the reflection operator, the rotation operator, and also the projection operator. So if we know all these things very clear, then we can actually uh, do the matrix diagonalization techniques. Okay, so thank you for your kind attention in this particular lecture, and we'll see you in the next lecture. Thank you very much.